Good morning, Kim. You're still not on Wi-Fi.
Because this doesn't work
For you.
for me.
What?
Yeah. It doesn't
Sorry,
work.
I'm on mute. Good afternoon.
Yes, hello. Let me reduce the voice. I'm testing a new configuration for the audio, so we're gonna maybe make you speak a little bit to see how it works.
Okay.
Go ahead, Kim. Can you talk? Can you say something?
Yes. Can you hear me? Can you hear me, Raul?
Did you have any problem with the communication at all?
Before with Wi-Fi? Yeah. No, that was okay. Like with Wi-Fi,
Okay.
it was okay.
Jabot, can you hear me from ETS? Jabot.
The video is still, huh?
The video is, the video quality is not good.
Oh, this is the Wi-Fi stuff.
This is the Wi-Fi stuff, yes.
I wonder whether we could have used the actual computer here.
This thing here.
Yeah, just connect there, and I should have tried that and have one fixed setup that works all the time, as opposed to having it from laptops. So who we have here? We just have.
We have Toronto. We have ETS. I think Laval connected as well, but no one is present yet.
Hi, this is Laval.
Hello, ETS. Can you? Okay, we have Laval too. Can you say something, anyone? Because we want to try a new audio configuration here.
Sure, you're sounding good so far. Very clear.
Not hearing anything.
I'm not hearing anything. Did you vote?
Anything else you want me to say? Is that good enough?
Okay.
ETS, can you, hello from ETS?
Volume. Yeah.
Okay, adjusting the volume. Again, ETS, can you say something?
Yes, hello.
Hello?
Can you hear me? No?
Yeah, we hear you. I'm just adjusting the volume here. Keep going. Say something, please.
Hello from ETS.
Okay. What, you guys hear him clearly?
Yes.
All right. I think works okay. How about you, Laval?
You are sounding good, and I am curious to find out what you tried.
Okay, I think we used to have an issue hearing, in particular, Toronto from here. So today I'm changing the audio configuration and see maybe this will improve. So okay, we hear you very well, Leslie. That's very good. Who do we have in Toronto?
This is Thomas here. Can you hear me?
Hello, Thomas. Yeah, go ahead. Speak more a little bit.
Hi. Speaking right now. Yeah, can you hear me?
Can you speak again?
Can you speak louder or close to the mic, please?
Can you hear me?
Yeah.
Okay, great.
Go ahead.
Yeah, okay. I don't know what you want me to say, but good.
Okay, it doesn't have to be intelligible, you know. Say 1, 2, 3, count, do whatever you like.
Testing 1, 2, 3, testing 1, 2, 3.
Oh, very good, very good. Oh, okay, so I think we have a better audio throughout, which is nice. So we can hear you well, Toronto. That's the first time.
Okay.
Excellent. All right, so I think we have everyone. Are you all ready to start?
Yeah, I think so.
Yeah. All right.
All set?
Okay, excellent. So welcome everyone to this third lecture or lab, part of the module on network softwareization technologies and enablers. As you may suspect, this lab will be dedicated to network virtualization. Network virtualization was also the topic for those who are attending the principles and foundation module of the third lecture. Network virtualization is a concept that predates SDN and can be provided without SDN or network softwareization. But they can work. And actually, in this lab, will be dedicated to the conjunction of SDN and in particular, open flow-based SDN and network virtualization, and how they work together. Specifically, the topics that will be addressed in the lab will be open flow and open vertex. What did I say? Open flow? I said open flow. I meant FlowVisor, obviously. FlowVisor and open vertex. And these are two very prominent technologies for virtualization, leveraging SDN to do that. So without further ado, I'm going to leave the stage to Shihab, who will take you through the lab.
So hello everyone, and welcome to the end. So I've already uploaded the lecture notes for today on Piazza. So please download the notes from there, because we'll be using the commands and everything from the lecture notes. A quick introduction to network virtualization. The core idea is we have one single physical network, but we want to instantiate multiple virtual networks on top of this substrate network, or on top of this physical network. So this means that although we have a single network, but we will create slices out of this single substrate or physical network to different tenants or different users. And since this is focused on SDN, so in this case, the slices or the virtual networks, each tenant can have their own network controller or open flow controller to control their slice of the virtual network without interfering with each other. So that's the core idea of network virtualization, and when you conjunct it with SDN. So we'll be looking at two different technologies today. One is called FlowVisor, and one is called Open Vertex. Now, why we are looking at two different technologies? Because they provide different abstractions for virtual networks, how a virtual network looks like for that concept. So that's why we'll look into both of them and try to create virtual networks and control them with separate SDN controllers. That's the high-level goal for today's lab. So we'll start with FlowVisor. Now, FlowVisor by itself, it's an open flow controller. What it does is it slices up the flow space and assigns this flow space to each separate tenant or user. And each user can use their own controller to control traffic inside that particular flow space. All right. Now, before going into the details of how this works and whatnot, the first thing let's look at is what exactly is a flow space. Slicing a flow space, creating a slice of a flow space. So what exactly is a flow space? So if you recall from OpenFlow specification, OpenFlow defines a set of header fields that can be matched, right? So we can install flow rules inside switches, and flow rule can contain header fields, different values of different header fields. Those header fields, we apply some action. Now, a flow space is the all possible values we can have for all the headers in this header space or in the match space. That is, in this particular case, which is defined by OpenFlow. So let's take an example here. Like, for example, if we think that, okay, we can only match on source IP addresses and destination IP addresses, geometric representation of the flow space is like a plane in a two-dimensional space, right? where we can think of the source IP address as one dimension and the destination as another dimension. Then this whole plane, it contains all possible source and destination IP address pairs that we can actually have, right? Assuming there is a finite number of source and destination IP addresses, so find our flow space in this case. So this is the all possible values we can have for those headers. Now, slicing up a flow space means that we take subsets of values of those headers and create a subspace inside this whole flow space. So for example, if we look at the picture again, our whole flow space in this case is divided into 3 slices, right? We have an orange, a blue, and a yellow slice. Subset of source IP addresses, destination IP addresses, right? So this collection of the range of source IPs and this range of destination IPs, they represent our slice in this case. So that is what a slice is. When we are talking about creating virtual networks or slices in FlowVisor, this is for only 2 headers, right? Considering we have only 2 possible match fields. Now imagine we can have more than 2 match fields as defined by OpenFlow. In version 1, we had 10 possible match fields. So this means that we actually have a 10-dimensional space. In a 10-dimensional space, we can actually carve out a 10-dimensional hypercube, which will represent a flow, like a slice in this flow space. In OpenFlow 1.4, we have 4 match fields. So this means that we actually have a full space. And again, we can carve out a hyperspace out of this 41-dimensional space that will represent like a slice in our case. So that's the basic idea of a slice. So we have all possible values of our header fields. That is our flow space. And we take out subsets of values of each different field. And that creates a slice inside the flow space. Now, if we look at FlowVisor, how it works, the way it works is as follows. OpenFlow network. OpenFlow network is essentially a network of switches which support OpenFlow protocol. And then FlowVisor by itself, it sits as a controller and talks directly to the switches. Now we push all of our configurations to FlowVisor to define what are the different slices would be inside the flow space. So we define that of IP address and port number and input port. All of these, when they're combined, they create one flow space. So this way we configure FlowVisor to create different slices. For example, here we have these 3 slices, like orange, yellow. And then what we do is we take each slice and assign a different SDN controller to control a slice. So this means that each controller here, like this controller 1, 2, and 3, they can independently control each of these slices without interfering with each other. So for example, controller 1, it cannot control any traffic that matches like a blue slice. Traffic that matches only the red slice in this example. Same for controller 2, same for controller 3. So then what we have is we have an OpenFlow network. We know that, okay, what are our possible values? We slice them up and create this virtual view of the network, right? Virtual view of the network in this case is a subspace in our flow space. That's the virtual view. That's the abstraction we are using in this case. And we take this slice or virtual network space and assign it to an OpenFlow controller for its own control. So that's the concept of FlowVisor. So we'll be basically looking at this layer here, the FlowVisor layer. How can we actually configure this layer to create different virtual slices? And also we'll see that how we can use different controllers to control different flow spaces of the same network. The next goal. So any questions before I proceed? We're all good here? In other places, any questions? No? Yes? No?
I have a question.
Yes, there's a question from Waterloo. Yes.
So if we actually divide the flow space, for example, by the source IP address and destination address, no 2 hosts can have the same IP address, right?
Exactly, yes, yes. So the question here in Waterloo was that, say for example, we divide the flow space by source and destination IP addresses. Then this means that no two hosts, they can have the same IP address pair. The answer is yes, because the in this case, the flow space partitioning is not transparent to the virtual networks, because each virtual network gets a piece of the global flow space. So that piece is excluded from the other virtual networks, so they cannot use that part. That's one of the limitations of FlowVisor. But the next technology that we'll look into, the Open Vertex, that actually eliminates that limitation. Yes, another question from Waterloo. Mm-hmm. Okay. All right. So the question here in Waterloo is how the isolation is provided. So for example, say OpenFlow Controller 2 tries to control some traffic that is supposed to be controlled by OpenFlow Controller 1. The answer is FlowVisor intercepts every OpenFlow message. And it implements the policy that, okay, who can control which part of the traffic. So even though, say, Controller 2 issues OpenFlow message that is modifying a flow rule that it is not supposed to do that, then FlowVisor will drop the packet. Excuse me. Then FlowVisor will drop that particular OpenFlow action. So it will not be installed on the network. Does that answer your question? Okay, all right. Then moving forward, so now let's start our VMs. So the installation steps, so the FlowVisor has been already installed on the VMs. So we don't have to go through like all of the installation steps. We just need to go through the first step. So the thing is, for our last lab, we upgraded our Java version. FlowVisor is quite old. It doesn't really work with latest Java version. So we will like reconfigure our Java to use our like an older version before proceeding. So let's go to the VM. And open the terminal. Is it big enough? Everyone can see my terminal? From the back, like everyone can see my terminal? Okay, all right. So let's first reconfigure Java to use an older version. So I have provided the command here in the slide. So let's just copy the command and try to run it here. So when you run the command, you should be able to see a list which looks something like this with options for using different versions of Java. Assuming that you were able to successfully install Java 8 during the last lab. Can everyone see a list like this here in Waterloo and as well as in other places? Yes, no? Okay. ETS, Laval?
Yes.
Yes, okay. So if everyone can see this list, then I think in my case, option one is an older version of Java, Java 7. So I'm selecting option 1 here, but this number might be different on your machine. So select a Java version, which is not Java 8, like an older version, 6 or 7, depending on which one is installed in your machine. So most likely it will be 7. So we are using an older version of Java now. So it should be good to go now. All right. Now, rest of the installation steps, again, it's installed on your VM. If you want to install it later on another VM or on a physical machine, just follow these steps. It should be fine. So slide 7 is something learned from experience. If you don't do this, it really doesn't work. It uses a database at the back, but if you need to give like all right permission to the database for FlowVisor to work. This is just a hack. I've put it here in the slide. Maybe use it next time if you want to really install it somewhere. Okay, so the first thing we'll do is, so FlowVisor comes with a default configuration file, which can work pretty much out of the box. We don't really need to modify anything. So we need to first load the configuration file. So let's load the configuration file. That's the first command I'm going through. To load the configuration file, we use this command fvconfig or FlowVisor config, and this is actually the path to the configuration file. So okay, didn't give any errors. And then, so once the configuration is loaded, let's start FlowVisor. So FlowVisor is installed as a service in Ubuntu. So let's start FlowVisor from init.d. And before doing that, let's make sure one thing: whether any other OpenFlow controller is running on the system or not. Just in our case, so okay, all right. Okay, let's check this thing. Okay, so let's first quickly check if any other OpenFlow controller is running on the system or not, because by default, OVS comes with like a default controller, like a reference controller. When you boot up your VM, that controller runs in the background. So let's kill the controller. And it should be the PID here. Okay, let's. Okay, so if you run this command on your CLI and see that there is an instance of an Open vSwitch controller running, then run the next command from your CLI to kill the controller. No? Okay, it's called OVS controller. Sorry about that. Okay. So let's kill the controller and try to check if. Okay, all right. So there is no controller running on the system at this moment. So we loaded the configuration file, killed any other controller that was running on the system, and let's now start FlowVisor. Okay. So to start FlowVisor, run this command from your CLI. And after running this command, check the status, whether it is running or not, by just changing start to status. If FlowVisor is properly running, then you should be able to see an output, which is something like this. You should see an PID for FlowVisor. So did that work for everyone? So for if FlowVisor started properly for everyone here in Waterloo and other places as well? Yes? No? Okay. All right. I got 2 thumbs ups. ETS?
There is one problem here with one guy from ETS. Can you come to explain?
Yeah, the controller, I couldn't kill the controller. Can you repeat the command, please?
For? Sorry, I cannot. Can you come closer to the mic? Oh, for killing the controller. Okay. Can you see my screen?
Yeah. Yes.
Where this thing.
It's running again. There is no controller running. There is no controller running. You don't have control. Just this command you put it. This one.
No, just I'll put here.
Okay. No, I think this is one. This command is just a mention. This is related to the result of this one, which needs following this one.
Is it right now?
Yeah, okay.
Okay, all right, so let's proceed. Okay, so once we have FlowVisor up and running, so let's enable one service of FlowVisor that we'll need for creating virtual networks, which is called a topology control service. So there is this command called fvctl, which stands for FlowVisor control, used throughout the rest of the lab. So this will be used to create the slices, assign flow space to slices, enable, disable services, and whatnot. So first of all, we need to enable this service called topology control. So I have the command in the lecture notes. So let's execute the command. All right. So did everyone get an error? Pretty much everyone got an error. All right. Now, again, this is something. There is a solution to the error, which is again a trial and error thing. So what happens is in the back end, FlowVisor uses a database. And whenever FlowVisor tries to modify something in the database, it acquires a lock. The lock itself is a virtual file in the file system. And sometimes there are issues with the permission of the file. And because of that, FlowVisor cannot lock the database. In those cases, FlowVisor usually fails with this error. So let's remove the virtual lock files first. So the commands are given in the slide. I think this is one file, and there is another file. There are two commands, two files. So after removing the files, let's restart FlowVisor. So the command for restarting is the same as starting it, but instead of start, we put restart. Okay. Now, after restarting FlowVisor, let's try to. So after restarting FlowVisor, so after removing the two files that is mentioned in the slide, and after restarting FlowVisor, let's run the fvctl command again to enable that service. Now it should work for everyone. We should not see any error. Is it the case for everyone here in Waterloo? Yeah? Other places? Good? All good? Okay. Toronto, Laval?
Yes, from it, yes.
Okay, thanks. Laval and Toronto? Yeah, I haven't received any green signal or anything from the other two places. Is it working okay? Okay, all right. Okay, all right. So then moving on. So now we have the configuration stuff taken care of. Let's try to create slices from a network. So this slide actually shows the topology we are interested in, and the slides, and the slices that we want to create. So we'll start with a very simple topology. So what we have is a linear topology of 3 switches, S1, S2, S3. Each switch has a host connected to it, H1, H2, and H3. right? So we'll create 2 slices out of this network. The first slice is a blue slice, which will which will be used to enable communication between host 1 and host 2, H1 and H2. And the other slice, the red slice, will be used to handle communication between H2 and H3, right? So as you can see, in this case, the notion of virtual network, it is defined on the flow space itself, right? Not necessarily on the nodes or the host or the links. So we have actually an overlapping host in this case. But again, the way we define the flow space, it will isolate the communication between these 2 pairs of hosts. So just to recap, we have this simple physical network, and we'll create 2 slices out of this physical network. One is a blue slice, another is a red slice. So the blue one will be enabling communication between H1 and H2 only. So this means that H1 will not be able to communicate with H3 when we are using like the blue slice. And again, like the red slice, it will enable communication between H2 and H3. So the steps of creating a slice are, so first we create empty slices using FVCTL. Once we have empty slices, then we create flow rules, like rules which are very similar to flow rules, to partition the flow space, to create these sub flow spaces out of the whole flow space. We create these sub flow spaces and assign them to these empty slices. So this way we populate the slices, and that's how we configure the slices. All right. So then next slide, we first deploy a topology. In this case, we're deploying a linear topology. Let's just copy the code from here. So I'm opening another tab and deploying a topology with Mininet. So it's a linear topology with 3 switches. I'm populating the ARP table and also using MAC option to have like nice MAC addresses. For the controller, I'm specifying it will be using a remote controller with IP address as the local host and port as 6633. So this is the port where FlowVisor is listening for OpenFlow messages. So for the network, we define FlowVisor as the controller to use. And then FlowVisor will intercept all the OpenFlow messages that will be later on exchanged between the slice and the other OpenFlow controller. So let's first deploy the network. All right, so we have the network deployed. Let's go back to another console and let's try to see if it. All right, so this command, this subcommand for FVCTL lists data paths. It will list all the switches. The hypervisor, sorry, not the hypervisor, the FlowVisor has recognized. So all the switches that has connected to FlowVisor. So as we can see, we have 3 switches, right? Switch 1, 2, and 3. So these are the DPID or data path ID of the switches. All right, so everyone deployed the network, and they were able to see from FlowVisor that it recognized all the switches. Did that work for everyone? No issues? Okay. Other places, no issues?
Excuse me?
Yes.
I have 4 switches. I don't know why.
You have 4 switches?
Yeah. I don't know. 1, 2, 3, 4.
So more people have 4 switches.
Can you?
One possibility is there was a OVS bridge already created on your machine that was not created part of Mininet. OVS switch created on your machine. So okay, let's try to do one thing. So from your CLI, if you run OVS vsctl show, what do you see? Oops. So from your CLI, if you run sudo OVS vsctl show, do you see 4 bridges? S1, S2, I think I see S1 here, S3 here, S2 here. So if you see 4 switches from your list data path, like your data path list, then it is very highly likely that there is an additional bridge here under OVS that was created somehow before and not cleaned up properly. So in that case, what you can do is, so bridges S1, S2, and S3, so they are created by Mininet, that's for sure. If you see something else, try to delete that.
We're fixing now. Yeah, he has another switch, so just have him to delete that switch. So everything is okay now.
Okay, all right. So it worked for you. Okay, all right. So here in Waterloo, if you're seeing the same thing, like more switches than you're supposed to see, you can just do this thing. Run this command like OVS vsctl delete bridge del br, and then specify the name of the bridge that you're seeing like extra that is not supposed to be here. You can delete that bridge. That bridge, it should be fine because there is no link to that bridge or to that switch from the other switches. But just in case, for consistency, if you want to delete that, you can delete it like that. But otherwise, it should be fine. All right. So now first, let's create 2 empty slices which doesn't have any flow rule or flow space assigned to it. Let's get back to our slide. I'll explain what the command does. Let me just copy it here. All right, so this command, this subcommand of fvctl add slice, it will create an empty slice. So we specify the subcommand and then give this slice a name, right? It can be like any textual name. In our case, we are giving the slices these names blue and red. Then the next parameter here is what is the address of the controller that will control this particular slice. So later on, we'll deploy 2 more controllers in our virtual machine, one on port 7000, one on port 8000, and they will be assigned to different slices. So when we're creating the slice, we have to specify where will be the controller running, right? So this is the address here. And finally, at the end, this should be the email address of the administrator who is controlling the slice. For the time being, let's just put a dummy email address. So it will ask you for a slice password. So for the time being, let's leave it empty. And everyone should see something like this, that the slice blue was successfully created. If that is the case, then let's create another slice, red. This will be controlled by a different controller, which is running on TCP port 8000, which we will later run. And well, we can keep the fake email address same, or we can change the fake email address here. So this will create another slice. Let's leave the password empty. So this will create another slice. So we have 2 empty slices right now, all right? So once we have the empty slices, let's now create the flow rules to divide the flow space and assign them to the slices. You can actually have a look at these slices by running this command. But I don't think that's necessary since they were successfully created. Okay, so before adding the rules, let me just quickly explain what is the format for adding like a flow space to a specific slide. So the format is we'll be using fvctl command, and there is a subcommand called add flow space. So with this subcommand, we'll first define a flow space and then say that, okay, where we want to assign this flow space to. So first we give a name to the flow space. So the name is just for identification. It can be a textual name. Then we specify a DP ID or a data path ID, because the network consists of switches, right, or data paths, and each switch has a data path ID. Now, when we define a flow rule, we have to specify, okay, for which particular switch, which particular device does this flow rule apply to? So that's what the DPID does. So this will be the ID of the switch for which we are writing this flow rule. Then there is a field called priority. Again, the idea is if somehow we end up creating overlapping flow spaces, then the priority field will act as a tiebreaker between these overlapping flow spaces. So in this example, we'll not be creating overlapping flow spaces, so we can have the same priority for everything. Yes? So a question here in Waterloo is that is a data path always a switch, or can it be something else? So a data path is a device that is built using open flow specification in this case. So usually it is called open flow switch. So I was at priority. Okay, then the match field, the match part. So this match part is exactly the same as we saw when we manually installed OpenFlow rules into OVS bridges. So this match part defines the flow space. Okay, what is the value of this field? What is the value of that field, and whatnot? And at the end, we say that what is the slice that is responsible for this particular flow space? And each slice can have different permission on the flow space. It can either act as like a read-only slice. That is, it can only read packet ins from that slice and cannot do anything on that particular slice. It can be a read-write slice for that controller. This means that for that part of the flow space, this means that this slice can actually modify flow rules inside this flow space. So there are these different permissions, and there are permission bits. So for the time being, we'll allow both reading and writing to the slices, to the flow space for a slice. All right. So before going through all these commands, let's get back to the picture on slide 9 a little bit to see how exactly are we defining the flow space. So let's take each switch and see what would be the flow space inside the switch. So for switch 1, now what we're trying to do is with this blue slice that it will handle any traffic in this switch S1 that is coming on this port 1 from host 1, and the destination is host 2, right? That's one thing. So on switch 1, on port 1, if any traffic comes on port 1 from H1 and the destination is H2, then that part of the flow space, it should be assigned to this blue slice. Similarly, again on S1, on port 2, if there is an incoming traffic from H2 that has an IP address of H2 and the destination is the IP address of H1, then that should also be assigned to the blue slice, correct? Right? Makes sense? Okay. Now, again, similarly at switch 2, we look at the ports and the incoming traffic and the source and destination IP addresses. So for port 2, the source IP address of H1 and destination of H2 that belongs to the blue slice, and also the reverse traffic as well. So then to define this blue slice, what we need to do is we go from switch by switch, take switch 1, take switch 2. For each switch, we look at the ports and the characteristics of the traffic on the port, and based on that, we create a slice, create a flow space, and assign it to this blue slice. All right. Similar thing is happening for the red slice as well. So for instance, here for S2, if we see that, okay, there isn't traffic that is incoming on port 1 and the source IP is H2, but the destination IP is H3, then it belongs to the red slice, right? This is how the traffic is differentiated between the red and the blue slice. All right. So similarly, for the red slice, we go from switch S2 and S3, look at each port and look at the characteristic of the traffic that is incoming on each of the ports. And based on the characteristic, we create a slice. We create a flow space and assign it to the red slice. So that's the high-level step of how we create the flow spaces and assign it to the slices. Now, let's translate this high-level idea into actual commands, actual supervisor commands. So I am on slide 12 right now. So let's take the first command. Let's take the first command and try to execute it. Okay. So before executing it, let's try to understand what exactly is happening here. All right. So we are running this add flow space subcommand, right? The first parameter is a name for the flow space. Again, this is a name for identification. For convenience, we are calling it blue flow space 1 or BFS1 for short. And then the two numbers are, the first one is the DP ID or data path ID of the switch. And the next number is the priority of this particular rule or flow space entry. And then we actually have a match. So what is the pattern of the traffic that should match for this blue slice to be activated, right? So now the question is, first of all, how did we get this DP ID? Again, okay, let me just go to another. So when you list the data paths, it shows you the actual DP ID of the switches, and also at the same time shows you the internal mapping that FlowVisor uses. So FlowVisor uses like shorter numbers or like shorter names for the DP IDs. So we can actually use these numbers as well when we are specifying the data path ID in our command. So here I'm using that number, like a small, like just one, not like a long version of the DP ID. All right. For priority, I'm putting 1 here. I'll be putting 1 in all of the rules because we don't have overlapping flow spaces here. So the priority is the same. And then the match rule here. So the match rule says on switch 1, switch with DP ID 1, match any traffic that is incoming on port 1. The IP source is this 10.0.0.1, and the IP destination is that, like 10.0.0.2, right? Now the question is, where did we get all these numbers? Let's get back to Mininet. Just to refresh our memories, when you run net actually shows you which interface is attached to which host, right? So for switch 1, this interface S1, ETH1, it is attached to the host 1. All right. And if we do a OVS OFCTL show on S1, it will show you the port numbers here, port 1, port 2, and what does port 1 represent? So port 1 is an enumeration of this S1 ETH1 interface. So that's how we know which switch is connected to which which host is connected to which switch via which port. So again, coming back here, input port is 1. Host 1 is connected to switch 1 on port 1, input port 1. We have the source and destination IP addresses here. Again, from Mininet, we can figure out what are the source and destination IP addresses. Can I clear here? Okay, no. So it would be something like pi-h1.ip. It will show you the IP of a host 1. Similarly, pi-h2.ip, it will show you the IP address of host 2. Right? So this way we can obtain the IP addresses of the source and destination pairs. So this is the anatomy of a single rule that we'll be adding. Right? So we have the match field here. And then finally, at the end, we specify which slice is responsible for this subflow space. We're assigning it to blue slice. And as I said before, each slice can have different permissions. So permissions usually have like a 3-bit number. Each bit can be on and off. And based on and off, it can be read only, read, write. The other permission I don't exactly remember at this moment. But the important ones are like whether it can be read only or it can also modify anything in the flow space or not. So 7 means all the permission bits are enabled. So that's one entry we added, right? So this actually corresponds to, let's get back to the slide. If we go back to figure 9, the rule that we just added, it corresponds to this thing here that, okay, we have this switch S1. Any traffic that is incoming on port 1, source is H1 and destination is H2. So this is one rule that we added. So similarly, let's add the other rules as well. All right, so let's take the second rule. This one is for reverse traffic. Yes, so this one is for reverse traffic on switch S1. So first we added like traffic incoming on port 1, and then now we added a rule for traffic incoming on port 2. So that's the reverse traffic. I guess that's pretty much for switch 1. Sorry, I'm on slide 12. So this is for switch 1, and then for switch 2, similar rule. We add rule for traffic for each port. So this is a DPID2, which represents switch 2, and we are adding creating a flow space which matches traffic on incoming port 2 and with specific network source and destination. And let's add the next one. All right, so these flow rules, these four rules, like in combination, they define the flow space that this blue slice is responsible for. So we have defined all of them at this moment. Now let's create more rules and assign them to the red slice. So up to this point, it went okay for everyone. No errors or anything. Okay, other places, I got okay from ETS, like Toronto, Laval. Did it went okay? Okay, got thumbs up from Toronto. How is it going? Okay, Laval, it went okay. All right, it's fine here. Okay, yeah, I have a question here. All right.
Why did the first command not show anything like adding request ID?
That's a very good question that I also had in my mind. Probably it's just an implementation thing. So the question here was, why didn't the first command showed an output like this one? Like for the subsequent commands where it said that, okay, there was a flow space added with a request ID something. Most likely it's an implementation issue. Otherwise, there is no other explanation that I found. All right, so we have the blue ones added. Now let's add the red ones. So that would be the next slide, slide 13. Again, not much to explain here. Very similar to the blue one. We just go by switch and port by port and define the flow space in that way. Okay. I probably should have put it in a script, but anyway. Okay. All right, so just copied the commands from the slide and put it in, like executed them to add the rules for the blue ones. Now, so at this point, we should have 2 slices which are up and running, right? And we should be able to assign different SDN controllers to different slices, and they should work theoretically. So let's check if they work or not. So let's run the OVS controller, the reference OVS controller on, okay, did I do? So let's open like 2 different windows, 2 different tabs. So let's run one controller on port 7000. So OVS controller is the reference controller that ships with OVS. Let's just run the basic one on port 7000 is in us. Should be running. Let's go to another tab and run it on port 8000. Remember to change the port, otherwise it will tell you like there's a port conflict. Okay, so 2 different controllers are running. So from H1, let's try to ping H2. All right, so from H1, we were able to ping H2, all right, which is the expected behavior because both of them part of the blue slice, so they should be able to talk to each other. Let's try to ping H3 from, let's try to ping H2 from H3. Again, it's working. Again, it's the expected behavior because they are part of the same slice controlled by the same controller. And the controller should be able to set up a path in between them. Now let's try to ping H1 from H3. So this should not work. That's the expected behavior because H3 and H1, there is no slice that is handling this particular flow space, that the communication between H3 and H1, right? There is one slice that is ensuring that H1 and H2 can talk. There is another slice that is ensuring H2 and H3 can talk. But there is no slice that that defines the communication between H3 and H1 and assigns that to a controller, correct? So this should not work. And is it the same for everyone? Here in Waterloo? Yes, yes. Other places? Okay, all right. 2 thumbs up from ETS, all right. Went okay in Toronto. Laval? Okay, all right. So that's the pretty much for flow visor that we'll go through. So again, the basic idea is that the abstraction that flow visor provides us is more like a flow space, not really virtual networks consisting of virtual nodes and links that we have seen in the lecture, but more like a piece of the flow space. If you think about flow space as a space, in this case, a slice, it controls a subspace in this like the bigger, larger flow space. We were able to create different flow spaces, assign different controllers to different flow spaces, and enable communication in between them. Right? So let's try to do an exercise. Let's see if that works or not. So let's go back to figure 9. Now we had 2 slices, right? Red and blue. Let's try to create, as an exercise, create a green slice between H1 and H3. All right. So it will be something like, okay, let me see if I can change it on the fly here or not. Oops. Okay, maybe not a good idea. Maybe Okay, just give me a second. So it should be something like this. Wow. So can everyone see my screen? Okay, maybe it's better to do it like this. So try to create a slice, which is a green slice. So, and the green slice enables communication between H1 and H3. So the green slice, it will, to define the green slice, what you need to do is you need to specify on switch S1, S2, and S3 the characteristic of the traffic incoming on different ports and how that will be assigned to the green slice. So try that as an exercise for the next 15 minutes, just to refresh what we just saw till right now, to get an idea of how to write these rules and assign them to different slices. So try to go through the exercise. If there is any question, interrupt me. So I have a question here in Waterloo. I'm just repeating that for everyone. So the question was, does FlowVisor work with ONOS controller? The answer is theoretically yes. Because you can deploy any controller with FlowVisor. It will work. Yeah. But here, in our case, in this specific case, it will not work practically because ONOS requires an updated Java version, like Java 8. And FlowVisor doesn't work with newer Java versions. So in the same VM, it will not work. But again, you can deploy ONOS on a different VM or in different container on a different machine. So that will work there. So is everyone doing okay at other places? Right. So if there are no questions or anything, then we take a short break before starting Open Vertex, the next thing. So maybe 10 minutes. If anyone wants to go to washroom, get a coffee or something. So we'll take a 10-minute break and resume at 1:25.
Shihab,
Yes.
can I have a question about the homework?
Yes. Go ahead.
Because in the assignment you said that we can use REST API to from the owners to get the network topology, but then in the description it also said that there's no any forwarding application installed. So without the forwarding component, how can the owners get the topology?
Okay. Sorry, I'm trying to hear the question. Can you please turn it down a bit? Okay. Can you repeat your question, please?
Yes. My question about how the owners can get the network topology if we don't install the forwarding application.
Okay. So for your testing purposes, what you can do is you can have the forwarding application at the beginning, do an all pair ping to discover all the hosts, and then remove the application and clear up the flow tables. For testing purposes, you can do that. But you can assume that when the assignment will be tested in a test script, at the time when the assignment will be tested, there will be no forwarding application installed. So only the application that you will be writing will be installing forwarding rules into the switches. Does it answer your question?
So you mean that at the beginning we can install the forwarding to get the topology, and then we remove?
Yeah, you can assume that. Okay, that there is a phase where the topology is initialized with the necessary applications and whatnot, and after that, those applications are unloaded.
Okay.
Or deactivated.
Okay, I get it.
Right?
Okay.
Okay.
Thank you, Sal.
Okay. So we're taking a short break, and otherwise, unless there is any question regarding the short assignment, we're taking a short break, and we'll resume at 1:25. Yes.
Is that a cast steal somewhere?
You can. It's okay as long as you just reference it, because that's not the main part of the assignment. If you have a library or something, you can use it. There is a JSON C library, as far as I recall. I think so. I think there is a JSON C or something like that. let's resume the class.
Yes.
Okay. Although ETS is pretty much empty. It's all right. So, all right, we're resuming the class in like a minute or so. Okay, so the next thing we'll be looking at is Open Vertex, or OVX for short. Now, fundamentally, it is similar to FlowVisor in the sense that it allows this creation of virtual networks on an SDN, although it has different abstraction compared to FlowVisor, and allows this using of multiple controllers, like different controllers to control each virtual network. So we can create virtual networks out of a physical network and assign each virtual network to a different controller. And the controller, they will not be able to interfere with each other. If there is virtual network 1, controlled by controller 1, the controller 1 should not be able to interfere with a virtual network 2, which is controlled by a different controller. Now, so just taking a step back, like a limitation in FlowVisor was that the partitioning of flow space is not transparent, right? As we said before, if we take a part of the flow space out and assign it to one controller, then another controller, it cannot really use that part of the flow space, right? For example, if we take a source IP prefix and assign it to a virtual network, another virtual network cannot use the same IP prefix for the source addresses. So that's one limitation of FlowVisor, that this non-transparent slicing of the flow space. And also, like FlowVisor doesn't really provide this notion of virtual nodes and virtual links, right? The abstraction is that, okay, I take out a subspace from the big flow space and assign this subspace to a controller. The controller decides how traffic will be forwarded in that subspace. But the network view, from that controller's point of view, is still, to some extent, the physical network's view. It knows that, okay, this is the DPID of the switch, actual physical switch, and whatnot. So it doesn't have this notion of abstraction of virtual nodes and virtual links, which can have a different connectivity than the underlying physical network, right? So this kind of abstraction is not present in FlowVisor. So OVX, or Open Vertex, it solves these issues. So Open Vertex, first of all, it provides this abstraction of virtual networks, like full-fledged virtual networks with virtual nodes that has virtual ports connected by virtual links. And also, it allows these virtual networks to use the full flow space. So the slicing here is transparent. So the virtual networks, they're not aware of, I mean, this means that two virtual networks, they can have use the same IP address, for example, same IP address space for their source or destinations. So that's the advantage of Open Vertex, or OVX. Now, in terms of architecture, it's very similar to FlowVisor, that it sits in between the other OpenFlow controllers that are controlling the virtual networks and the OpenFlow network itself. And it intercepts the messages, the OpenFlow messages. Not only does it intercept the messages, it also modifies the OpenFlow messages and the flow rules that are being installed on the switches. to make sure that each virtual network has a complete view of the network while at the same time not interfering with each other. So for example, if virtual network 1 uses an IP prefix, then virtual network 2, which is also using the same IP prefix, OVX will ensure that whenever a flow rule consisting of these IP prefixes from different virtual networks are installed on the physical network, they are remapped to something else. And OVX internally maintains all these mappings. So for all the open flow messages, it intercepts the messages, it maintains the mappings, modifies the flow rules to ensure that there is complete isolation between the virtual networks. So that's how it works from a very high level. Now, so what would be the steps of creating these virtual networks in OVX? So if you have seen the third lecture from the other course, the theory course, usually there is a virtual network embedding phase when we instantiate or create a virtual network, right? Because usually what we have is we have a substrate network or the physical network, in this case the open flow network, and a virtual network that has virtual nodes and links, and the topology can be different from the substrate network or the physical network. So what virtual network embedding does is it finds a mapping between where the virtual nodes should be placed and how the virtual links between those virtual nodes should be created. That's the output of a virtual network embedding algorithm. Now, by default, OVX does not do the embedding for you. So it doesn't, I mean, again, by default, because there is a non-by default mode where we can do some sort of embedding using OVX. So by default, OVX assumes that there has been a phase before instantiating the virtual network that has determined that, okay, this virtual node should go to this physical switch. This virtual port is mapped to this physical port. This is how the links in between the physical virtual ports will be created, so on and so forth. So this is assumed. Now, given that we have this information that this embedding, what OVX does is it steps to create the isolations, create the virtual ports, connect them using the links, installs the necessary flow rules along the paths, intercepts the flow rules for different controllers, so on and so forth. So that's where OVS places itself in. All right. Now, the steps of creating a virtual network, well, there are many steps actually. So that's why, like a quick overview of the steps first, then we'll go through each of the steps to create an actual virtual network using OVX. So first, we create an empty virtual network that doesn't have anything, no virtual switches, no virtual links, nothing. Then we add the virtual switches inside these empty virtual network. Not only the virtual switches, because remember we said we know the mapping from the beginning that, okay, where does the virtual switch map to? Which physical switch does this virtual switch map to? So we use this mapping information to add this switch mapping to the empty virtual network. Once we add the switch mapping, the next phase is to create virtual ports on the switches and map them to physical ports. So when I say port, I actually mean the interfaces, right? The hardware interfaces that is carrying the traffic. That's the next step. Then the third step is to connect these ports to create an actual virtual link, to provision a virtual link. And finally, only adding switches is not enough. We also have hosts, right, which are the endpoints. We connect the hosts to the virtual switches as well. So these are the steps that we will follow to create a virtual network in OVX. Now, before going into the steps, let's have a look at a figure to have a better idea of how things are working. So for example, we have a substrate network here, which is a tree topology, right? It's one 3-level tree, assuming the first level is level 0. So we have a tree topology here with a few hosts, and we have a virtual network request here as well, right? A virtual network that has 3 virtual switches, and 2 of the virtual switches, they are connected to one of the hosts. Now, this host will be one of the hosts from the existing set of hosts that we have, right? You can assume that this is very similar to creating virtual machines in physical servers, and those virtual machines are kind of being connected to virtual switches. So if we look at virtual switch 1 or V1 here, this virtual switch has 2 ports, right? One of the port connects to V2 or virtual switch 2, and another port that connects to V3 or virtual switch 3. Similarly, V2 and V3, each of them has 2 virtual ports. One of them connects to a virtual switch, and another virtual port connects to a host, like one of the hosts. So again, the first step is to determine where would this virtual switch be placed to or mapped to. So that is output of the embedding algorithm. So for instance, in this case, say the output is that V1 should be mapped to physical switch S1. V2 should be mapped to physical switch S3, and V3 is mapped here to physical switch S6, right? Now, that is the first step, that is the switch mapping, right? This virtual switch is actually this physical switch. That's the mapping. Then we also need to map the ports as well. You see, like this virtual switch 1, V1, or this virtual switch 2, V2, it has 2 ports. So one of them connects to a host, H1, which is here on the substrate network. So in that case, the virtual port that connects to H1, we map that virtual port to a physical port on switch S3 that connects to H1, right? That's the mapping. If that's the mapping that ensures that there is like a valid communication channel between the host and the virtual switch, right? That's the mapping phase, output of the mapping phase. Similarly, we figure out the mapping of the ports for this virtual switch V1 on the ports of this physical switch S1 to ensure that this virtual link between V1 and V2, we can actually create this virtual link, right? So in this case, we map the ports on appropriate ports on the switches and create a path through the network. Creating a path through the network means that OVX actually installs forwarding rules in the network to make sure that this virtual node V2 can talk to virtual node V1, right? And also, OVX ensures that from the virtual node's point of view, this path does not appear to be a path. It appears to be a link, right? So the virtual node doesn't see that it is going through a multi-hop path, right? It creates a tunnel with an encapsulation to make sure that the virtual node sees the path as a virtual link, like a single link, one hop link. So then the controller that is controlling this particular virtual network, when it will do a topology discovery, it will not see these underlying details of all these paths and whatnot. From the controller's point of view, it will see a 3-switch topology with 2 links, right? And the links will be like a single link, not like a multi-hop path. Any questions up to this point? Yes, one question from Waterloo. Yes. Yes, of course. One assumption is that, of course, like the question was, does the physical switch has to be OpenFlow enabled or not? The answer is yes. Assumption is that our network in this case is OpenFlow enabled. If it is not, then OVX doesn't work, right? Any other questions from in other places? No? Yes, no? Okay. All right, then let's proceed with creating this specific virtual network topology. So we'll deploy a physical network that looks like the one shown here. And then we'll provision this virtual network on top of this physical network. All right, so that's the goal. So before starting OVX, let's first disable or stop flow visor so that there is no interference. Okay, so all right, sudo etc init Visor stop. All right, so we stopped flow visor. Let's stop mininet as well. All right, so we are not using the previous topology here. Excuse me. And the flow visor is stopped. So OVX has been already downloaded inside the VM. So I think if you look at the home directory of the VM, you will see a directory called Open Vertex. So this is the root directory for Open Vertex, and inside this directory there is a directory called scripts. Let's go there and let's execute. Okay, so before doing that, I think we started some OpenFlow controllers, right, for the previous demonstration and also for doing the assignment. So let's stop the OpenFlow controllers. Because we'll be starting the OpenFlow controllers again to control specific virtual networks here. So we stop the OpenFlow controllers here. Nothing else is running. Just checking if mininet cleared everything. All right, so I don't have anything here. All right, so inside this directory, there is this script called ovx.sh. It might be the case that this script doesn't have execute permission. In that case, just give the script execute permission like this. Change mode, give all like execute permission on the script. And then let's run the script. All right, so if everything went okay, then we should be able to see like a series of like a sequence stream of outputs. If something went wrong, probably we'll see some exceptions. I hope no one saw any exception. Oh, you did. Okay, all right. So what did you see? Because sometimes, like if you have another OpenFlow controller running on the same port, you can see an exception for port conflict. Did you check?
I checked.
Can you please double check? And other places like no exceptions. Okay. So running this script essentially starts this OVX service, and OVX service exposes a REST. So OVX also ships with other tools, that is a wrapper around the REST APIs that talks to this OVX service using the REST API, but provides a more easier way to use that rather than writing long URLs and trying to debug it. So we'll be using one of those tools. So let's change. Okay. Before doing that, let's deploy our network as well. So we are deploying a tree topology using mininet. So we're deploying a tree topology, specifying the depth as 3 and fan out as 2. We're branching 2 ways all the time, running it with ARP and MAC options. And again, controller is remote with 6633 as a port number, the TCP port number where the OVX is listening to. Let's start it. Okay, so mininet started. If you go back to OVX console, you'll see like like a stream of outputs with a lot of error and warn and whatnot. Don't worry about it too much. So OVX sends a lot of LLDP packets to discover the topology. It just keeps logging a lot of output regarding those things. So we have Mininet, and if we just do say we ping from H1 to H2, it will not work. Because although OVS is an open flow controller, but it doesn't have any path setup application or anything. It acts as like a middle layer in between actual controllers and the network itself. So it will not set up any path, although it will receive packet-in messages to forward this packet-in messages to other controllers. If there is no other controller, there is no one to set up the path, right? So it will not work. So as expected, H1 ping H2, it doesn't work. Now let's try to create the networks. The first step, let's create an empty virtual network, right? So what we'll be using is this particular tool called OVXCTL. It's a Python script that ships with OVX. That's a wrapper around the REST API, as I said before. And it allows us to create, like perform different operations, like creating a network, adding the switch mapping, creating ports, connecting ports, and whatnot. So the format for creating a network is something like this. So we run this script, this control script, with this option to create a network. And then we specify, similar to Flowvisor, what is the IP and port number of a controller that will be controlling this network, responsible for this network. And then for this network, what is the IP prefix that will be assigned to its hosts. And then what is the length of this prefix? So this is something similar to like an IP address / a number. It just takes it separately. So what essentially does this command do here is it creates a network and tells OVX that this network will be controlled by a controller running on port 7000. And the network address for the host that will be in this virtual network is something like 10.0.0.0 with a IP prefix length of 16. That's what we are specifying when we are creating a virtual network. All right? So let's try to create this virtual network. Copy this command. Go to a different window. Okay, so now the question is, where do we find these scripts, right? These wrapper scripts. Let's go to OpenVertex, utils. So this directory actually has these different scripts that we'll be using, right? So for the time being, we'll be using this OVXCTL script or OVX control script. Okay, so all right, so I copied the command from the slide, executed it. If it is successful, it will show an output something like this, that a virtual network has been created and it will print some metadata about the virtual network. Now, there is one particular metadata that we are interested about, and we'll actually need that when creating subsequent entities like virtual links and whatnot. That is the tenant ID. So tenant ID is similar to like the virtual network ID. So what is the ID of this virtual network? So as you can see, the tenant ID, it is listed as the last item in this JSON object, right? So there is nothing, usually tenant ID starts from 1, 2, 3, 4, keeps going like that. So for our virtual network, we have a tenant ID of 1, right? So right now we have a virtual network, which is empty. There is nothing in it, right? No switches, no links, nothing. So let's try to add the switches one by one, the mapping of the switches one by one, right? How do we do that? Let's go here. Okay. So to add the mapping of a switch, we again use the same wrapper, OVXCTL, this OVX control script, but now use it with this subcommand create switch. So create switch will, excuse me. Okay, not me. All right. Sorry about that. So OVXCTL, when we run OVXCTL with this subcommand of creating a switch, it will add this mapping between a virtual switch and a physical switch inside this virtual network, right? Because right now the network is empty. There is nothing in the network. So we're now adding the switches where the virtual nodes are mapped to. And how do you do that? We run this create switch with first and tenant ID. So tenant ID will be used from now on everywhere. And then the physical DP ID or data path ID of the switch. Yes, sorry, go ahead.
Can you create a switch without mapping it? Just like do the mapping later.
So a question here in Waterloo is that can you create a switch without mapping it by doing the mapping later, right? The answer is actually no, because OVX doesn't. It always assumes that the mapping already exists.
Because in previous class there was something about like allocating or like there's sometimes like an algorithm or something in order to determine it. You may have like you want to just create your topology for the virtual network, and then but you don't actually know how you're going to map it because of like allocation. Use the algorithms in order to determine what the best thing is. So is it possible just to define what your virtual network topology is and then do the map later?
Okay, so the question here is like during the I think that was during the last lecture for the theory part, right? Yeah, during the last lecture of theory part, there was I think content that addressed this virtual network embedding, where we are saying that okay, create a virtual network and then find a resource allocation for the virtual network on the physical network, and then instantiate the network, right? And now the question here in Waterloo is, can we just create a virtual network and find the mapping later? The thing is, so OVX comes actually after this virtual network embedding part. So you have an abstract representation of your network with resources and everything. You run your virtual network embedding algorithm. That algorithm determines where does everything go, right? Where does a switch will be placed, which path will be used to create the virtual link, so on and so forth. Once you have that information, OVX uses that information to actually create those things in the underlying network. Yes, so that's the answer. Any questions from other places?
No from ETS.
No from ETS. Okay. Toronto, Laval, are you on the same page up until now? Okay, I don't see any response from other places. Like, okay, all right, yeah, all right, yeah, I now see response. All right. So, okay, so we created a virtual network that's empty. Now let's add some switches from the physical network to this virtual network. So the syntax is we use this OVXCTL script, right? Create a switch, specify the tenant ID, and then the DP ID of the mapped switch, the data path ID of the mapped switch on the physical network. So how do we get the data path ID? Well, we can get it from Mininet, right? Oops. So, like from Mininet, we can get the DP ID of all the devices, like for every object, like switch 1, S1, S2, and whatnot. They have this DPID attribute, which stores the DPID, but it doesn't show it in a formatted way. Ideally, like every two nibbles, they should be separated by a colon, a semicolon, to show it like a formatted in like a MAC address. But anyway, what we'll do is we'll use the commands from here. So if we go back to slide 18, what we see here is these 3 virtual nodes. They are actually these 3 physical nodes, right? Switch S1, S3, and S6, because that's where they are mapped to. So let's add these nodes in our virtual network first with their DPID. So let's copy a command. Again, switch S1, S3, and S6, they have DPID of all 0, then 1, all 0, then 3, all 0, then 6. Oops. Nope. Here. So let's add the first virtual switch. Yes, as you can see, it says that the virtual switch, it has been created. Shows you a tenant ID, the switch ID. Now here, there is a different ID to the switch, right? So we added a physical switch here, but again, like when we added it internally, OVX considers it as a mapping of a virtual switch, and it assigns a different DPID to the virtual switch to distinguish it from the physical one. So here you will see a switch ID that is completely different from what we added. So that's the virtual switch ID, right? This will be used later on. We'll see when it is used, but that's the idea. So let's add the other switches as well. Switch 3. Okay, added the other switch, again assigned it a different virtual switch ID. And finally, the other switch with a different virtual switch ID as well, right? Now, so let's see if, so, okay. Yes, there is a question here in Waterloo.
Here we are assuming that through virtual network embedding, the switch 1, 3, and 6 have been mapped for the switch.
Exactly. So the question was more like a clarification that we're assuming that through virtual network embedding, the virtual switches to the physical switch mapping is already known. Yes, the answer is yes. All right. So if the switches has been already added or not, right? So if we run OVXCTL with help, it will actually show the possible commands that we can run with OVXCTL. And there are a few, like a set of commands like get something that like queries internal database to obtain information about specific entities like devices, virtual networks, virtual ports and whatnot. And it will show it on the console. So let's try to run this command, get virtual switch mapping. The way to run this command is OVXCTL. We run the Python script. Okay, if you notice one thing, we are always running it with this -n option, and this means that no password. There is actually no password set for OVX, but every time you run it, it will ask for a password. So -n disables that. Then get virtual switch mapping and the tenant ID, because we are querying what are the virtual switch mapping for virtual network 1. If we run it, we'll get a JSON object in return, right? So this JSON object shows you what are the virtual switches we have in this virtual network and what are the physical switches these virtual switches are mapped to. So for example, this is the first one. This key is the DPID of the first virtual switch, like one of the virtual switches. And this indexes this object which shows you which switch does it map to, right? So this DPID is the DPID of a physical switch, right? This is most likely the first mapping that we added to. Similarly, there are like other virtual switches here as well. Now, there is one thing that you notice here is, so this is an array. This is not a single object, right? Switch mapping was supposed to be like a one-to-one mapping. You have a virtual switch. It is mapped to a physical switch, right? But here it is shown as an array. And also there is an attribute called links, which is empty here. What OVX allows is, it allows to create a big virtual switch out of many physical switches. So for example, say your virtual topology is that you just want to connect a few hosts with a big virtual switch. You don't really care how the traffic is routed internally. In those cases, what is possible is that when you create a virtual switch, we can specify multiple switch IDs, like physical DP IDs. And in that case, we'll see like multiple like entries here under switches. And under links, what we'll see is like the set of links that connects those switches, right? To ensure that traffic can actually route between ingress and egress of that specific virtual switch. All right. So for the first example, let's go through a simpler one and create like a one-to-one mapping between the switches. We'll try to deploy multi-switch mapping at the end if time permits. So anyway, so we added 3 switches. They are present here when we are querying the internal database. So that's working okay. Now what we need to do is we need to add ports to these switches. All right. Yes, and there are a lot of ports, unfortunately. So the way we create ports is that, again, we use this control script, and we use this subcommand create port, specify the tenant ID as usual, and then specify which physical port should be included in our virtual network, right? Because again, we are including all the possible mappings in our case. So we specify the data path ID of the switch and the actual physical port number of the switch that should be included in the virtual network. So if we get back to slide 18, just to clarify the picture, say for instance, switch S1, right? Switch S1, okay, let's take switch S3, then maybe it's a bit easier. So let's take switch S3, for example. So it has 3 physical ports, correct? They are numbered from 1, 2, and 3. Now, will all of them be included in the virtual network? No, because this one, like this port that connects to host H2 is not part of the virtual network, right? Only this part that is connected to host H1 and the port that is used to provision this path with S2, only these 2 ports will be included in the final mapping, in the virtual network mapping, right? So what we do is, through this create port command, we include the necessary ports. That is the outcome of this mapping. The mapping said that, okay, these ports will be used to connect this to this, right? So we include those ports into the mapping and specify that. So that's the idea. So for S1, there will be 2 ports, definitely. Port 1 and port 2. It has just 2 ports. For S2, it will be 2 out of the 3 ports it has. Similarly, for S3, it will be 2 out of the 3 ports. And same for S6 and S5, right? Now, what we need to do is we need to identify the ports, right? Which port numbers will be actually used in the mapping. So let's take a command and have a look how it was identified. So I'm back to slide 21 again. So let's, for example, take let's, for example, take switch 3 as an example. So in this example, what we're doing is we're creating a port through this control API and including physical port number 1 and 3 from physical switch 3, right? How did we figure out that it would be 1 and 3, not 2 and 3, or not 1 and 3? So let's get back to Mininet again. Or okay. So let's get back to Mininet again. I'm running net, which will show us the links, the network links, and let's select switch S3, right? So S3 has 3 interfaces, right? ETH 1, 2, and 3, and they are numbered from 1, 2, and 3, like physical port number 1, 2, and 3. If you do a like OVS OFCTL show, you will see that sequence. So S3 ETH1, which is port 1, that is actually connected to a host, right? And that's what we want. So that's one port that we want. So port 1. S3 ETH2, that's connected to another host, but we're not interested about this host, right? Because this is host. This corresponds to host 2, which is not in our virtual network. And finally, we have port 3, that S3ETH3, which is connected to switch S2, right? Another interface of switch S2. Now, this is a port that we want, right? Because we want to provision this red path. Red path in slide 18, right? We want to provision this red path. So for S3, we want the port that is connected to host 1 and the port that can provision this red path, right? So these are the two ports. And from Mininet's output, it seems like this is port 1 and port 3. So that's how we figure out which ports should be included in our mapping. All right. So now let's create the ports then. Oops. Okay, so I'm copying the commands from here. So the first two commands, they are for switch S1. Again, switch S1 has just 2 ports, so there is no need to like figure out which ports to connect to. We just add both of the ports in our mapping. Port 1 has been created, 1 port, and again, like port 2, we add another port here as well. Then we add ports for switch 3 here. Switch 3 port 1 and switch 3 port 3. And then ports for switch 6. Similarly, if you do the exercise, you'll figure out that for switch 6, we also need port 1 and 3. All right, so we're taking it from here and adding it here. Okay, so we have added all the ports that was required. Right? So at this point, what we have is we have the virtual switches, the mapping. Oh, sorry, there's a question. Yeah, go ahead.
What happens if you create the port twice?
You can do that. You can share a physical port between multiple virtual ports. Yes, you can do that.
Like, I ran the first command like twice, and it said that it created another virtual port. Is there a way to remove it?
Oh yes, there is a way to remove it. If you go to help, I think there is an option called remove port, remove virtual port.
Oh, okay.
Okay, let me just show you. So okay, so there is a question here in Waterloo. So what if you accidentally add a port twice? So let me just show you how to remove it. So there is a subcommand called remove port. Right. So what you need to do is you run this thing, run the control script. Oops, sorry. Run the control script with remove port, and then specify the tenant ID, and then it will ask you actually for the virtual switch ID and the port ID. Right. So the virtual switch ID, you can see from the output what is the virtual switch ID where this port was added to, right? And also the port ID. You can use this combination to remove the port. Right. So just in case anyone has like just executed a command twice and added one port like multiple times, you can use this subcommand remove port followed by the tenant ID followed by the virtual switch ID and the port ID to remove that port from the virtual switch. Right. Just in case. Okay, all right. So now we have virtual switches with ports. So essentially, what we have here is, if we go back to slide 18, we have these nodes provisioned. Now we need to provision the links, right? We need to create the links. So which means that we need to connect the ports between themselves. So let's connect the ports then. Okay. The way to connect the port is this subcommand called connect link. So what we do with connect link is that, okay, before proceeding with connect link, so was everyone able to like create the virtual switches and all the ports? with no errors or anything? What for everyone in Waterloo? Okay, other places? Okay, all right. Okay, all right. Then I'm proceeding with the link creation. So once we have the port, we use this subcommand called connect link. Right. So connect link essentially takes a pair of source and port ID and the destination switch ID port ID and creates a link in between them. So the format is as follows. First, again, we specify the tenant ID, and then we specify what is the source virtual switch ID. Right. Now, since we're now connecting using links, we are using now virtual switch IDs. We take the virtual switch ID as the source. We also specify what is the port number of the virtual switch, the source virtual switch that we want to connect to. Then we specify the destination virtual switch ID, the link's other endpoint, and similarly, what is the destination port, right? So we take, say, for example, virtual switch 1, port 1, and put a link between that virtual switch and port with virtual switch 2, port 2, for example, right? So this is how we specify a link. And after that, we specify that, okay, although now, again, this is a virtual link, right? But it will be provisioned as a physical path in the network. So what is the path computation method that OVX should use to create the path? So one option is SPF, or shortest path first. So in this case, OVX knows that, okay, this is the endpoints mapping, source mapping, this is the destinations mapping. Just create, like, provision the link along the shortest path between these two physical switches. That's one option. There is another option called manual, where we can specify a specific path by a sequence of physical switches and physical ports. All right. That can be useful. Say, for example, there is an external embedding algorithm that has determined a specific path to embed the virtual links. In those cases, we can use that thing. Otherwise, in this case, we'll be using shortest path first method. So we're not specifying the path explicitly. OVX is computing the path internally. All right. So it will be creating the virtual link along the shortest path between the physical hosts, physical switches. Followed by this argument, we can also provide another thing, which is, will there be any backup path for fault tolerance of this virtual link? Say, for example, we put 2 here. Then what OVX will try to do is it will find 2 more shortest paths, which is disjoint from the first one, to make sure that if the first one, something in the first one fails, there is still other paths where the link can be routed. Now, in our graph, we don't have any alternate paths, so we'll put a 0 for now, right? So, excuse me. So let's take a command, for example, here. Again, what we're doing is we're connecting the link between this virtual switch ID here, its port 1, with this virtual switch ID with its port 2. Right now, the point is, how do we know, like, which virtual switch to pick and which ports to pick, right? So for the virtual switch, we know that because we already saw that there's a way to see the mapping. So which virtual switch corresponds to which physical switch, it can be obtained, right? Where's my mouse? Okay. So this is same as running this command. It will show that, okay, this is virtual switch ID. This is mapped to this physical switch ID. Now there is another one. It's called get virtual ports. Oh, wait. Okay, sorry, not get virtual ports, get virtual topology. Yes. Okay, no, not this one. Sorry about that. I missed something. Oh, right. Yes, yes, yes. Right. Yeah, I also actually faced the same problem when preparing for the tutorial. So the thing is, there is actually no API, at least API wrapper, that returns you the list of virtual ports. The thing is, when you create the virtual ports, the ports are sequentially numbered in the order they were created. So what happens is that when you create the virtual ports, it actually returns a JSON object. So if we are programmatically creating the ports, we can store JSON, keep track of which port is what, scroll up to one of the outputs. I think that would be easier. Yeah, here, for example, so when we were adding these like switch 6 and port 3, right, it created a virtual port ID for this particular port, like particular physical port. And it is actually returned in the output, like the JSON output. So what the JSON output contains is that it contains the switch ID as well as what is the new port ID, the virtual port ID of that specific physical port, right? But when the problem is when we're doing like the thing with through CLI, there is actually no way to like query that and figure that out. So let's try to rely on the order here. So the order would be, if we go back to our figure on slide 18. So for virtual node 2, we added its first port, like port 1, the physical port, like of S3, like port 1 for port 3 second, right? So this means that port 1 will actually be the port to connect the host. And port 2 is actually the one to create the link with switch V1, virtual switch 1. So that's why if we go back to slide 23, and we're actually connecting sorry, not this one, sorry. So slide 22, we're actually connecting the port 1 of switch 1, there's the top switch, with port 2 of switch 2, right? As we like figured that out right now from the figure. So we take the command and execute it. So it will automatically compute the shortest path under the hood and create a virtual link. So we have a virtual link. Again, the virtual links are also assigned IDs, like sequentially from 1, 2, 3, 4, and again in the order they are created. So we create one link, similarly create the other link, right? So this is the link between V1 and V3. That is the one we are creating right now. Okay, so we created the virtual links. Now we have the switches mapped their ports, connected the ports in between switches to have the switched network. Now we have to attach the hosts to the switches, right? Remember, like there were 2 hosts that were connected to the switches. We need to attach them right now. And again, for V2, the host will be attached with port 1. Similarly, for V3, the host will be attached to its port 1, like virtual port 1. All right, so again, we can attach host using this connect host subcommand. For that, we specify a tenant ID, then the data path ID of the switch. Again, this is the data path ID of the virtual switch. and also the virtual port number, followed by the host's MAC address. Right? Again, the host MAC address, we can obtain that from Mininet. So we take the command. So we're connecting, for example, here host 1 and host 5, right? These two hosts, host 1 to virtual switch 2 and host 5 to virtual switch 3. Okay. We've connected one of the hosts. We have another host. All right, so now we have the virtual network and attach the host to the virtual network as well. So let's start a controller and see if we can actually send some traffic in the virtual network or not. So I'm on a different tab. I'm running this OVS controller, the reference controller, on port 7000, like before. All right, so the controller is running, no errors here. So although we have created the virtual network, we have to explicitly start the virtual network. You have to tell OVX that now start the virtual network, make the network operational and running. Otherwise, it will just not work. So let's start the network. Again, it's a simple subcommand, start network. Okay, so network, this virtual network at this point should be operational. So let's try to go back to Mininet and try to send some ping messages. So from host 1, let's ping host 5. And the expected behavior is ping should work, right? Because host 1 and host 5, they're part of the same virtual network. And there is a controller that has been assigned to this virtual network that is setting up the path. So host 1 should be able to ping host 5. All right? Now, let's try to ping something else. Say, for example, host 6. That should not work because there is no controller that has been assigned to a specific slice and where we can set up a path between host 1 and host 6, right? So expected behavior is it should not work. So was everyone able to do all of this, like create the virtual network, add the switches, the ports, the links, the hosts, and then start a controller and send some traffic? Did that work for everyone? Any questions up until now? In other places, any questions like did everything work for everyone? Any hiccups or issues?
Yes, from me, just a question.
Yes.
So basically, the on-off host cannot pin each other, and when we run some create some virtual node and virtual switch and virtual link, the OBS will install the rule on the open vSwitch. Is that right?
So can you please repeat your question just once again?
Yes, so I think that the OBS will install the rule, the forwarding rule onto the open vSwitch so that the S1 can pin the other.
Okay. Yes. So this OVS controller that we just executed. So from that OVS controller's point of view, it actually sees a virtual network with 3 switches and 2 links and 2 hosts. So it will try to install the rules on those 3 switches to make sure traffic can go through. But OVX will intercept actually those rules and translate them into something else and install those something else into the switches. In fact, let's go to Mininet console. And okay, let's ping H5 from H1 to make sure there is some flow rule installed on the machines. Let's terminate it and run something like this: dpctl dump flows. All right. So when you run dpctl dump flows, it will dump all the flow entries of all the switches. Let's just look at like one of the entries. If you go up and look at the entries for switch S1 here, and just take one rule for example. So as you can see here, we have this network source and network destination, these fields in the match, right? But if you look at the IP address, the IP address is not present in any of the hosts. Correct? Right?
Yeah.
Because for our hosts, it has an IP address from this 10 series. But in the network, the IP address is changed. So what happened here is definitely like this OVS controller. From OVS controller's point of view, it is getting these IP addresses in this 10 series, like 10 dot something. It is creating flow mode messages with that IP address, but these flow mode messages are intercepted by the OVX controller. And when OVX controller is intercepting those messages, it is modifying the flow mode messages in the entries inside the flow mode messages to make sure that they can use the same IP address without any conflict. So it is actually being mapped to something completely different, right? For example, like this IP address, it is completely different from what was in the actual like IP header. So this is how OVX does this virtualization. They call it IP address virtualization. So essentially providing each virtual network a complete view of the IP address space. But essentially at the back end, it is replacing those IP addresses, keeping a separate mapping between the original and the modified IP addresses. So this is why it is intercepting all those messages. Right? Any questions? And also, like, did that answer your question in ETS?
Yes, it did.
Okay, all right. Any other questions from other places? Okay, so there is a question in Waterloo that can a host be part of multiple virtual network or not? If the depends on the number of interfaces a host can have, it can be actually part of multiple virtual networks, right? Because if you look at from the host's point of view, if it has just one single interface, it has just one network, right? It can connect to just one network. If it has k network interfaces, this means that it can connect to k different networks. And we can actually connect the host to k different virtual networks in that case. That is entirely possible, yes. Because, pardon me? It depends on the number of interfaces. Yes, always it depends on the number of interfaces, yes. Depending on the number of interfaces, it can connect to multiple networks, yes.
As a comment, and the other way around is also true, right? So one switch can be assigned to two or more.
Yes, so one comment from Waterloo is that, yeah, one switch can be assigned to more than one virtual network, which is true, yes. As long as even one port can be used across, there are ways, yes. So essentially we are sharing the substrate network here, right, between virtual networks, and OVX is ensuring this isolation between the virtual networks. So definitely one switch can be shared between multiple virtual networks, yes. Yes, another question from Waterloo.
So if the host has only one hardware interface, but
yes,
it has two virtual machines inside it,
yes,
can those two virtual machines be part of two?
Okay, all right. So the question here is, if a host has one hardware interface, but it has two virtual machines running inside it, can the two virtual machines be part of two different virtual networks? The answer is actually yes. Usually in these cases, like separate tunnels are created, and these tunnels have different identifiers to identify different virtual links that are going through the same physical link. Yes. Now, in this example, you can actually treat the hosts in the same way as a virtual machine. You can consider that the host that is being created and attached to a network, just like a virtual machine. It has an interface, connects to the network. Again, there can be many layers, software layers in between that does many magic. like multiplexing multiple tunnels of different virtual networks through one single physical network interface card, that's entirely possible, yes. Any other question? Okay, all right, so if there are no more questions, let's proceed to the, I think that's the last thing I have. Okay, so this test worked. So now, so far, what we saw is that, like, if we want to create a virtual network, right, we have to specify every tiny details, right? We have to specify where does this port map to, where did this switch map to, and all these things. So now, OVX ships with a Python script that is called embedder. So embedder is a semi-automatic way of automating some of the stuff. Internally, it takes care of some of the details, so that we don't have to really specify like all the details through CLI. What it does is it takes a JSON file, and the JSON file contains the description of a virtual network. Takes the JSON file, translates it to appropriate configuration, and configures the virtual network in that way. So let's try to deploy another virtual network using this JSON API and see if that works or not. So now, okay, I think I should have mentioned that earlier, but so if you remember the GitHub repo we used last week, that GitHub in that GitHub repo, I added a sample JSON file that describes a virtual network. You can just what you can do is so if you have the repo in your machine, you can just do a git pull. It should update the source code inside your machine, or pull the new file here. So I already did a pull, and it's already up to date here. But for your case, if you do a git pull, it should pull the JSON file, the example JSON file on your machine. Okay. All right, so let's open the JSON file. I think it is called big switch vn.json. Let's just open the JSON file to see the format of an example virtual network, right? Okay, so the format is something like this. So first we specify an ID. So this is similar to the tenant ID, or the ID that will be assigned to the virtual network. If it is conflicting with existing IDs, it will not be used. It will be incremented to the next available virtual like valid tenant ID. So I think we already have a virtual network with ID 1. So let's put an ID 2 here. Okay. Then for the controller, we specify where to find the controller, like what's the IP address and port number. Again, it's running on the same machine. We are running it on port 9000. Not like port 8000 as before, because when we run embedder, it opens up like a JSON RPC interface for accepting these JSON objects. And that listens on port 8000. So we are using a different port here. And then, so the example of virtual network that we'll be using here is the one I said before, like with multiple switches, like one node mapped to multiple switches. So what we want to create here is something as follows. Let me get back to the picture. Maybe that would be easier. Wait. What is the request? 676. So we want to create a virtual network like this. Okay, let me. Yeah, I think I need to update the slides later on with the updated drawings, and I'll do that just after the class. So for the time being, let me just draw a virtual network. Say it is called, say, X1. That's the node. All right, and it is connected to two hosts, H7 and H6. So this is the virtual network we want to deploy. We just want one switch, like one huge switch that connects two hosts. That's the virtual network we want to deploy. So in this case, the node mapping would be something like this, right? Okay, maybe. Say we have a new virtual network that we want to deploy. It looks something like this. It has just one, it requires one virtual switch, this abstract notion of virtual switch, connected with this host 6 and host 7. You can consider it as VM6 and VM7, right, in a data center. Now, the link mapping is, the node mapping is something like this. The node mapping spans multiple physical switches in this case. Switch S5, S6, and S7. We have this VM or host H6 connected to one port of this virtual switch, and this VM or host H7 connected to another port of this virtual switch, right? Now, physically, these VMs are located at different places. So this virtual node, if we want to abstract the communication between the VMs using like a single virtual node, it has to span multiple physical switches in this case, correct? So this means that physical switches S6, 7, and 5, like a one physical connected component that can route traffic in between the two ports. So that's the idea. So, but here when we're specifying the request for the virtual network, we are not explicitly specifying which set of physical nodes does this virtual nodes correspond to or map to. What we're specifying is that, okay, these are the set of hosts that we want to connect together using a big virtual switch. So, and what are the hosts? This is one of the hosts with like host with MAC address this connected to switch that on this port, right? We are just giving the specification of the host. We are not giving any particular specification of the nodes here, the virtual switches here. So essentially, we're specifying that just connect host 6 and host 7 using a big virtual switch somehow. How? That will be determined by the embedder or the embedding algorithm. It will determine that, okay, since I need to connect this host and this host, where does the ports are actually connected? And if I want to make sure that I can route traffic in between those two ports, what should be the path inside the network, right? So then that set of switches, they will encompass the node mapping of this big virtual switch. Yes, go ahead.
So if you don't specify it as a big switch, what will it do? Will it create like 3 virtual switches?
If you don't specify where?
The type as being big switch.
So are we, okay, if you don't specify the type as a big switch, then you need to specify more elements here. You need to specify what are the virtual switches you'll be using. Yes, in that case, yes. This is just an example, right? When you use the type big switch, so the question was, if you don't specify the type as big switch, then what happens if I just specify the set of hosts? The answer is, when you don't use the type as big switch, you actually have to specify all the virtual switches that will be present. Yes, only for big switch, you just specify that, okay, these are the set of hosts I want to connect using a big switch. I don't care where the big switch is or how the traffic inside the big switch is routed. All right? So this is like another level of abstraction for specifying the virtual network request. So here we're specifying the list of hosts here, like which physical switch they're connected to on which port. And you can see like there is another option here we're specifying, which is what is the routing algorithm. Because again, definitely like one big switch is mapped to multiple physical switches, right? Somehow we have to route in between the nodes, like the physical nodes. What would be the algorithm for routing that? We can specify shortest path first. So these are pretty much the parameters we specify, and then let's try to deploy this virtual network. All right. So what we do is we go back to one of our windows and start this executor. Okay, I don't think I put the command here, but anyway. So it would be something like Python embedder. Right, okay. So it should start and listen for JSON RPC requests. So let's start on controller as well. Okay, I'm running out of windows. Oops. So let's start the controller that will be controlling our new virtual network on port 9000. Okay, and then let's make a JSON API call, REST API call, sorry. Okay. All right. Do I have it here in the current directory? The answer is yes. Okay. So there was no error in the API call. It created a virtual network with this tenant ID. Let's try to go back to Mininet and perform a ping operation. So this should work, yes, because we attached H6 and H7 using this virtual network, right? So they should be able to talk to each other. But again, if we try to talk to H6 from H1, that should still fail, although communicate with one host connected to the same switch. Not necessarily should be able to connect, talk to all the hosts on the same switch, right? Because the virtual networks, they are isolating these two different hosts. All right. So I guess that's pretty much it for the lab today. So up to this point, any question from the very beginning, including FlowVisor and the steps for creating a virtual network using OVX? Any question, concern, confusion? From Waterloo? None? We're good. From other places, like was everyone able to do like all the steps, create the other virtual network using this REST API call? Did that work for everyone? Any questions from other places?
We're good here.
You're good at Toronto, okay. ETS, Laval. Okay. Laval, I don't see any response. So if there are no more questions, then that's pretty much it for today. I'll update the slides with the figures that kind of I drew on runtime, and we'll post them on Piazza. And also, there'll be another assignment for this lab as well that will be uploaded soon as well with instructions. All right. So yes, there's a question from Waterloo. Pardon me?
How do I byte all the memory of somebody?
There is a subcommand called remove virtual network. You can use that to remove the virtual networks. So there was a question on how do you wipe out the created virtual networks. There is a subcommand, remove virtual networks. You can pass the tenant ID. It will remove all the virtual networks. All right. OK, then hopefully next week there will be a different lab, I guess. But I'll still be here as a TA. So probably see you next week. All right. So if there are no more questions from other places, I'm disconnecting.
Thank you, Chahab.
OK. All right.
Sorry,
Bye-bye.
wait.
All right.
We have
Yeah, go ahead.
another question.
No, just post the video as soon as possible if you can.
Okay, so we just asked if you can post this video as soon as possible after
Post, pardon me, sorry, post what?
this video. This
Post
video.
this video.
Yeah, the recording.
Wait, so was I supposed to record it or someone else?
I think Kim did. Maybe Kim did.
So we talk with
I think it was being recorded from ETS,
okay,
right?
we're gonna talk with our professor.
Okay, all right, okay, all right. Talk to.
Okay.
Okay, yeah, bye.